Hello everyone, we're back with another episode of Computer Vision Talks, and this time we're going to discuss all about medical imaging, not really autoencoders, generative modeling, and yeah, a lot of things. So we're going to discuss the paper using unsupervised progressive context encoders for anomaly detection in digital melanoma pathology with Quincy. And the good thing is that the code is available on GitHub, and we'll be sharing the links in the YouTube video of the recording today. And let's know a little bit about Quincy. So Quincy is a second-year predoctoral student at the Mayo Clinic College of Medicine and Sciences. And his primary interests are in medicine and engineering. He's also worked as an undergraduate research assistant at the University of Minnesota, where he did research on colorectal cancer patients' survival analysis and breast cancer MRI image processing. His previous research experience is what motivates him to pursue his interest in the domain, and he intends to be a medical researcher. And I'm sure there is a lot that we're going to learn today. And please feel free to drop in your questions in the chat box. We'll be taking all of them in the end. Thank you so much for joining us today. Over to you, Quincy.
Thanks for the introduction myself. So today I'm excited to present our recent work titled Using Unsupervised Progressive Context Encoders for Anomaly Detection in Digital Melanoma Pathology. Okay. So before we discuss the details of this work, I would like to first acknowledge all the members and collaborators contributing to this research. As this study is supported by both the Mayo Clinic and Google, our team members include Dr. Ryan Gillett and Sandia from Google Cloud, Dr. Moreau and Dr. Float, who are the senior board certified pathologists from the Mayo Clinic Department of Laboratory Pathology and Medicine. Dr. Stephen Hart, Naresh, and me are from the Mayo Clinic College of Medicine and Science. So now let's start with the interesting parts of today's presentation. Skin cancer is the most common cancers in the United States, which includes the basal and the squamous cell carcinoma and the melanoma as the three common types. Compared with basal and squamous cell carcinoma, melanoma has a higher mortality rate, even it only accounts for 1% of all the skin cancers across the United States. Now the question that the computational biologists usually think about this is, could we build a model to differentiate melanoma from the normal skin using the hematoxin niacin, which is H&E stained whole cell images? Well, they probably could build a binary classifier trained on the whole cell images from both the normal and the melanoma classes, which could be used to determine whether a given test site is a melanoma or normal. However, another question comes, does this classification approach could be clinically useful? Absolutely not. One challenging is there are 9 types of melanomas recognized by the World Health Organizations, or WHO. If we anticipated the well-trained binary image classifier could accurately identify all the 9 subtypes of melanomas from the whole cell images, we need to make sure that we have sufficient whole cell images from each of the 9 types of melanomas for the model training purposes. However, to acquire a large amount of whole cell images from each of the 9 types of melanomas to train the binary image classifier is challenging in reality. In other words, if the training whole cell images missing or not having enough slides from certain subtypes of melanoma, the model will be less likely to make correct predictions on the whole cell images from those subtypes of melanoma cases. The other challenge is there are thousands of types of skin conditions. Melanoma is only one of them. Spitz nevus is another type of a benign skin condition. When training the binary image classifier to differentiate melanoma from normal skin histology, whole cell images containing the Spitz nevus will not be included in the training samples. In other words, Spitz nevus will be one type of anomalous skin histology and never seen by the model during the training process. If we deploy such a model into clinical melanoma diagnostics, if a given site includes the Spitz nevus, our model is more likely to make a wrong prediction on such slide, which will downplay the diagnostic accuracy and result in a misdiagnosis for the patients. So in addition, what about something else? Like this fun example you see here on the right, there are two lovely dog pictures within the skin histology image, which we all know this is impossible to happen. However, the question we have here is, what could be the prediction made on such image by the binary image classifier? Since this kind of image has never seen by the model during the training, the model should only make a random guess on the final prediction for this image, which will be more likely to make the incorrect prediction decisions. To tackle these clinical relevant challenges, we would like to try a different algorithm approach rather than the classification, which is the anomaly detection. Instead of a classification model trying to predict whether a given site is melanoma or not, we intend to train an anomaly detection model on normal skin histology whole site images only, which could learn the features of normal skin histology and then to differentiate the abnormal skin histology from the normal. Therefore, this anomaly detection model could highlight the suspicious regions from the images without providing the information about what types of anomalies they are. This could allow the pathologist to super focus on the highlighted region rather than searching from the entire site. Ideally, this could save a significant amount of time for pathologists to make the final diagnostics and really improve the clinical melanoma diagnostic practice. Now I would like to walk you through the significance of the study. As you see in this first picture, this is a workflow of the conventional pathology practice, which we also name it as the qualitative pathology. This requires the pathologist using a microscope to make the diagnostic from the glass slide. However, by taking the benefits of the whole site imaging scanning system, the glass slides now can be digitized and stored in the computer database. As you see the pictures in the bottom, this provides the opportunity for computational scientists to help building a computer-aided diagnostic tools by analyzing the digitized whole site images. Therefore, this research enables the transition from the qualitative pathology into a quantitative pathology practice. And now let's continue our discussions on the innovation of the study. Whole site image is a high resolution image with rich image contents. As you see in this example on the right, there usually are billions of pixels within a single whole site image. This will lead to a computational challenge, which is how could the model extract sufficient features from this kind of high resolution images without missing the important features during the training process. An incredible study led by Karis et al. From NVIDIA designed a new generative adversarial network architecture, which they name it as the Progressive Generative Adversarial Network, or PGAN. I will refer to the PGAN in this presentation. So before we discuss more details on this unique PGAN architecture, I would like to first introduce the generative adversarial network briefly, or GAN, to those who might not quite familiar with it before. So GAN is a deep learning framework intended to estimate the generative models while the adversarial process, which involves the two simultaneously trained subnetworks, the generator G and the discriminator D. During the training process, G intends to capture the distributions of the training data by generating the realistic fake data from a random latent space, but we also name it as a random vector space. Simultaneously, D intends to estimate whether a sample comes from G or the original training data set. Thus, G is expected to deceive D by maximizing the probability of D making a false prediction on whether a sample is real or fake. However, we expect D to be able to recognize the fake sample from G. Once both D and G are optimized after the training process, D should be able to generate a realistic fake data. Therefore, it could be used to recover the distribution of the input data. PGAN is the one unique GAN specific for high resolution image data. This architecture performs better in generating high-resolution photorealistic images compared to the other conventional GANs architectures, which makes it ideal to use with very large high-resolution whole site images. Similar as in the other GANs, PGAN includes two jointly trained subnetworks, G and D. G aims to generate photorealistic images from a latent space, and the D will then determine whether generated images are real or fake. To generate the photorealistic high-resolution images with satisfactory qualities, pGAN allows G and D to be trained gradually, starting from 4x4 resolution and 8x8 and 6x16 and up to 1024 by 1024. The layers will be incrementally added to G and D to allow the model to be progressively trained from 4x4 up to 1024 by 1024, which is increased by a multiple of 2, while keeping all the existing layers trainable during the entire training process. And this is the reason that we applied pGAN as the baseline model for our anomaly detection model architecture. The other novelty is that we leverage the pGAN to design this progressive autoencoder architecture. Basically, we take the encoder GE to project the input normal image into a Latin space Z during the training, and then decode the Latin representation using the decoder GD to generate the fake reconstructed image. GE then projected the reconstructed image into a so-called reconstructed latent space Z hat. The reconstruction error was measured between the Z and the Z hat. As we mentioned from the previous slides, we train the model on normal images only. This autoencoder model will train to learn how to encode and decode the normal host images properly. Therefore, we give the reconstruction error a new name, which is the normal error reference distribution. We also refer to as NERD. In clinical practice, if we train our pGAN baseline model on the normal slides from the Mayo Clinic, and the actual testing slide is scanned from a different hospital, which slides might have some differences due to the differences between the host image scanners and laboratory procedures. This may require we to retrain the model to make a good prediction. However, we train the entire pGAN model on such a high resolution host image is costly and time consuming. With the benefits of this autoencoder architecture, the NERD is trainable, and we could always require some limited number of additional normal slides from different institutions to only train this autoencoder model to update the NERD. Therefore, to adjust the baseline model's weights to make a good predictions on slides from the external laboratories. However, we have another concern that autoencoder architectures might only just doing the image compressions. And we don't want the reconstruction error here only determine how well the image compression algorithm behaves. So we leveraged a technique called image implanting, originally designed by James' teams to design this progressive context encoder, which we add the binary mask in the original input image and feed those implanted images into this progressive autoencoder model architecture. And we also train a discriminator in the end intends to determine if the generated images is real or coming from our autoencoder baseline by input this implanted images combined with the binary mask. So from now, I will start to discuss the training details of our progressive context encoder anomaly detection model architecture in details. We split the training into the 4 phases. So phase 0 is the pre-processing phase for phase 1 of the training, as you see in the slide. Melanoma mostly will rely on the epidermis layer. However, the dermis is the majority part of the skin, which includes a lot of collagen and fat tissues. To reduce the data complexity, we first pass the normal images into the Resonant 50 model pre-trained on the ImageNet, and then apply the principal component analysis, or PCA, to this collection of image vectors to project the vectors into a orthogonal basis. From there, the image corresponding to the first 80% of the first principal component was selected. We also did the manual inspections to confirm that those selected patches captures mostly epidermis, borders, and examples from each of the layers, whereas many images with collagens in a white space were removed. Across the 200 host images, there were 534,531 image patches in the pre-filtering set, and 4 to 7,625 post-filtering image patches. The phase 1 of the training is what we have discussed from the previous slides. It takes the normal query mask images as the input, feed into the generated D to generate the fake images GZ. Well, the generated G acted as a decoder at this time. The discriminated D will then determine whether GZ is real or not. Additionally, GZ will then be passed into the generated G again to project into a reconstructed letter representation Z hat, where the generated G now served as an encoder, noted as E. So the model has 3 losses to optimize the model's performance during training. The encoder loss will be computed as the differences between Z and Z hat. The generated loss will be computed as the differences between GZ and GZ hat, and the discriminator loss will be computed based on the difference between XR and XG. Phase 2 intends to learn the normal error reference distribution, or referred as NERD, which will represent the distribution from the normal samples. Therefore, the last phase of training we will calculate the Mahalanobis distance between the reconstruction error and the NERD, where we believe the distance will be small if the given images are normal, otherwise it will be large. In this phase, we will train the model to learn an optimal threshold to differentiate normal and anomalous distributions and flag the pixels greater than the threshold as the anomaly pixels. Since there are some single or less many pixels flagged out as anomalous pixels from the image, we do not want them to bias our predictions. So we also apply the kernel density estimation to only highlight the regions with enough number of anomalous pixels. When all the 4 phases of the training process are completed, we take the melanoma slides to test the model's performance. As you see in the inference pipeline here, we pass the query images into our well-trained model to compute the reconstruction error. Then the Mahalanobis distance between the reconstruction error and the NERD will be calculated and used to flag the anomalous pixels. Since the query images here are melanoma, which is the abnormal skin histology, the Mahalanobis distance between the NERD and the reconstruction error intends to be large. Therefore, we would expect to see a bunch of anomalous pixels being flagged out on the images. We will then apply the kernel density estimations to smooth those anomaly pixels and draw the finalized predicted anomalous polygons from the image to highlight the suspicious anomalous regions. As we have mentioned from the previous 2 slides, we have 4 training phases and an inference phase. Then we split and assign our total 209 host images with 200 normal and 9 melanoma slides into different phases. Since phase 0 of training is considered as the pre-processing phase for phase 1 of training, we assign the same 150 normal host images for both phase 1, phase 0, and phase 1. And then we evenly separate the rest of 50 normal host images and assign 25 of them to each of the phase 2 and 3 of the training process. And then we assign the rest 9 melanoma slides corresponding to all the 9 subtypes of melanomas recognized by WHO for the inference purposes. To ensure the model's performance, we have a senior dermatology pathologist annotated the slides and output annotated polygon images confirmed by another 2 pathologists, as you see on the left. And our predicted polygon image highlighted the suspicious anomalous region from the same slide as on the right. And then we mapping the annotated polygons with our prediction polygon images to make sure every pixel has the same coordinates within those 2 images. We define the true positive as the predicted polygon regions, which also fully within the annotated polygon. The false positive is defined as the predicted polygon region fully outside any of the annotated polygons. Then the true negative is the region that both not inside the predicted and annotated polygons, while the false negative is the region which not inside the predicted polygons, but do inside the annotated polygons. We will use these values to compute the sensitivity, specificity, and accuracy to evaluate our model's performance. However, as you have seen the pictures from the last slide, the annotated polygon covers a large tissue area. However, our predicted polygons are quite independent. As you see in this picture, the tissue in between 2 adjacent predicted polygons, which may also include some important anomalous tissue information, but never get the chance to be included inside the predicted polygons. So we apply the dilation method, which is to merge the adjacent predicted polygons into a single large polygon to address the problems we just mentioned. As you see in these pictures, we have gradually increased the dilation factors. The size of the single predict polygons also gradually expanded. And the large size of predict polygons will also benefit the pathologists, which do provide them a better diagnostic view from the slide. To better measure the model's performance, we also consider the impacts by applying the different dilation factors. As you see in this picture on the right, the sensitivity and the specificity of all the 9 tested melanoma slides are computed based on the different dilation factors. Each of the 9 tested slides are according to one type of melanoma recognized by the WHO. And we found the most optimal dilation factor before for all the 9 tested slides. In other words, with the dilation factor before, the average of the model was 94% sensitive, 87% specific, and 89% accurate. The details of the model performance were shown in this table on the left for each of the 9 tested melanoma slides, from A to the H. And this research also has some limitations. The first major limitation is the annotated polygon image provided by the pathologist only highlighted the tumor regions. Since it's challenging for pathologists to annotate all the anomalous histologic regions from the slide. However, our anomaly detection model intends to capture all the anomalous regions from the slide, which means the predicted anomalous polygons not only highlights the melanoma regions. Therefore, our final model performance matrix, computed based on the comparison between the tumor-only annotated polygon and the predicted anomalous polygon images, are not 100% accurate. If we could further get to the ground truth annotated polygon image highlights all the anomalous regions from the slide, our model performance matrix ideally will be changed and potentially could be improved. The last limitation of the study is the output predicted anomalous polygons only highlights the suspicious anomalous regions from the slide, but did not tell us what kind of anomalous skin conditions they are. But we could do more works to predict the labels of these highlighted suspicious anomalous regions by moving this research forward. So from here, I'll wrap up this research here and the presentation. And here's a slide for some of the reference. And you are welcome to check our paper, which is cited in the bottom, to get more details of the study if you're interested. And I would also like to thank for the 3 funding agencies to support our research. So all right, thanks again for joining my presentation today. I would like to take any questions from here and before we jump into the code review. Thanks.
Right. So yeah, from the audience, if you have any questions, please feel free to put it out in the chat section. Meanwhile, I'll ask a few questions that I have. Some of them might be related to the paper and other might be a little general questions. So when you talk about the normal distribution idea, from where did you come up with the concept of using a normal distribution? Because most of the anomaly detection paper that I've read so far work as tackling the problem as a classification problem, where all the non-anomalous or normal pixels are clubbed into one class and the anomalous pixels are clubbed into another class. So how come using the normal distribution?
So I will break this questions into 2 parts. For learning the distribution, that's why we want to change it into compare with rather than the classification problem. The reason is for the clinical use case. As I mentioned at the beginning of the slide, as a classification is not what we want. So we wanted to the pathologists super focus on this suspicious region, which that different looks like than a normal. So that's we leverage the GAN model architectures. So the GAN, which is generating the fake images based on the inputs, which intends to learning all the features that we can in order to generate realistic images. So, and we also say we adding the implanting techniques, just trying to avoiding the mode class problems most commonly when training the GAN architectures. So that's why we're thinking the GAN successfully learned all the variabilities of the normals. That's we can using the different distributions, using the reconstruction errors to differentiate the normal with any subtypes of anomalies. Does that answer your questions?
Yeah, it does. So another question would be, can you elaborate a little on the pre-processing and post-processing techniques being used here?
Oh, sure. So let me just go to the slides we talking about that. So people are probably gonna worry about this phase 0, right?
Right.
The two reasons here, the two steps, firstly, we are using this pre-trained Resonant 50 model. The reason we do that is because the image vectors here is we're talking about the high resolution, and usually just require large of memories to during the training and time consuming the costly reasons. So that's why we're taking those pre-trained models to project the images from the image space into a vector space, a feature space. And that's for first and down sample, the image sizes, training samples, and also we apply the PCA afterwards. So we think in the PCA is also the dimensionality reduction procedures. So, and we're taking the first 80% that contributing to the overall variability of the slide that we believe that will filtering out those of the features, the patches that we not expect to see them to reducing the complexity of the data. That's why, but we also concerned that does the PCA really behaves well as we expected? So we're adding manually inspections afterwards to make sure that we do filter out those patches we don't want it. Thanks.
Another question was from paper that when I was reading it, there was a sentence that masked images were used only during the phase 1 of the training, and for others we were using unmasked images. Can you elaborate why phase 1 needed masked images and other did not?
Okay, so the phase 1 training is basically doing the training the baseline GAN models. And also we mentioned before the mode types is the most common types, common errors when causing the GAN does not capture all the variabilities from the training samples. So now we're introducing the random mask images, adding to the original query images, and we're trying to determine the generated images also be realistic look, even you mask up some part of the images, but it still capture the features of what it's supposed to from the normal. But the rest of the phases is not, the idea of them is not training the GAN, because only the GAN model we train in the phase 1. That's the mask images we're only introducing and using in the phase 1 training.
Right. Talking about training the GAN model, was there, so when I was trying to experiment with fMRI data, and it happened that latent space worked better than the dense space as mentioned out in a lot of papers. Did you observe such kind of a pattern in your data set?
Yes, we do. So I believe that's this is sort of the experimental design problem. So what we really can, if you're really interested in this kind of topics, what we can do is we can set up the experiments to putting the image feature vectors space as a training groups, and you project it into feature space for another training groups to really determine which one performs better. So I believe that even the scan problems even have some sort of this kind of problems in the other data sets, but our data set is kind of unique, and which is not like the public available toy data set. Probably we're gonna facing into a different problems while training those kind of architectures. Right. But it's a really interesting important thing.
Understood. One last question from my end related to the paper would be that you said that having an additional network did not work well for you and just increase the training time. But additional network was used in a lot of other papers which were using GAN architecture primarily for anomaly detection. Why do you think it did not work out for your case?
So actually, we have tested some of the public available models when we really starting this kind of experiments. So they really fails on our satisfactions. The two major reasons I consider. The first is most of the using the game-based anomaly detection model, their input is a random vector space Z. So by here you see our input is a normal feature vectors. So by given random vectors, so the problems could be the gain is more likely to causing the more collapse problems. So the other challenge is some of the gain-based anomaly detection model, their optimization loss functions are only using some existing loss functions to optimize the model, and it does not try any of the regularizations, some other strategies in trying to mimic the overfitting things happens to this training process. And we all consider that the challenges and trying to avoid such a problems during our training. So that's where we come up with this sort of the unique architectures.
Right. Another question. I keep saying this is the last one, but I keep getting questions.
That doesn't matter.
The Mahalanobis distance is something I read for the first time because I'm fairly new to the domain. There was mentioned that it is using the color channel means. So if you have a data set with grayscale images like Brad's data set, brain MRI data set, you cannot use that distance metric on that, right? So which alternative, have you tried any other distance metric on that, if not Euclidean, because you said that Euclidean is not really suitable. So yeah, that's the question.
That's a great question, actually. So as we shown here, so we say the Mahalanobis distance because our images are definitely in the 4-channel images, which is RGB and alpha channel. So we won't run into any of the technical challenges using this Mahalanobis distance. So, but we in the real world implementation, we do leave this distance as the tunable hyperparameters options for the users. You can using the Euclidean distance as if you preferred, or you can using the other options. And also we leave that's not directly to your questions, but for the phase 3, as you all see here, the kernel density estimations, like we do the KDE, you can based on the centroid or based on the central. So those are all be tunable things by the user defined. It's not only hard coded says this is the only options we provide you. So we do leave you multiple options for what you prefer.
I'm sure this one is going to be the last question related to the paper, and that is that when you were saying about that you tried out GAN anomaly architecture to the whole slide image concept, it failed to yield acceptable images. So what does that mean? Even after iterating for different number of layers and everything, you were not able to reconstruct the images?
Could you rephrase the question a little bit?
Yeah, in short, what went wrong with GAN anomaly idea of applying it to the whole slide images? Or should I read out the line from where I'm quoting this? You write in the result section, we initially attempted to simply adapt the GAN anomaly detection architecture to whole slide images. However, the approach failed to yield acceptable images and was discarded. When you were exploring the images generated, you could find that it learned to encode only collagen and fat. So is it because they dominated the pixels, that is why it could just learn them? Because this is very common problem, like because even if you consider Brad's data set and you're trying to use an autoencoder on it, it ends up reconstructed mostly black images because only 7% of the pixels are non-black. So was it the similar problem with GAN anomaly detection?
So I think this is actually two problems involved here. So even it sounds like the more class for the GAN, but actually the two challenges we identify. The first one is definitely you mentioned 100% correct, is because the imbalanced data set problems happens here. As we just mentioned for the phase 0, that's why we're applying those pre-trained model for the embeddings and doing the PCA, because we're trying to filter out reducing the data complexity and remove some of the patches from the dominant classes. The other things is from the model training itself. So as we mentioned before, we're trying some architectures that are taking the random space as the input, but those kind of architectures really not behaves well, because that's usually happens is no matter what kind of the query images you give, the generated fake images always look the same. That's definitely the mockups happens. So what we think about is, could we instead of given a random space, we want to give in the real images. But for some reasons, the generated images might still not perfect. So we think about now let's do a little bit different. Let's give you some of the masked as in the images. We want to reconstruct exactly the same look in realistic images, even we cover some part of the images. So can you take a guess of what those images are, right? So then we combine all those three methods together, and it does solving the problems. So maybe if you change your data sets, you could run another problem that potentially are more technology available to tackle those kind of challenges.
So there's a question in the chat from Amok. He's asking, can you explain a bit more about the loss metric being used in nerd?
Sure. So as we said here, we have three kind of losses: the encoder, decoder, and discriminator loss. So all those things are based on the Vassarian gain losses being used by first introduced by the Yale. And what we do is we do a little bit different. Is we add in sort of the L2 regularizations to those loss functions, and we're also adjusting the weights of the loss. If you are really interested in that, we have the one supplementary the part in the discussion of the paper at the end. So we do introduce more details of how we apply different loss functions, different weights, adjusting that of cell composition being tested in these experiments.
Right. I hope that's better to you, Amok. In case you still want to continue the discussion, please drop in the chat and I'll let you unmute yourself. Next question is from Naim Mehmet. He's asking, how reliable is NERD as a template? Does a reservation loss can be rigorously modified to enhance scan performance?
So that's a really good question. And that's the major reasons we consider adding phase 2 of the training to introduce the trainable NERD. Because the two challenges here, so even you having training on, let's say, the 200 normal slides from the Mayo, but if with the Mayo says, next year, we're going to use a different device to scanning those images, color might look different. It's still normal, right? So the scanning techniques might be also different. Maybe we will create different pathology or cytotext to scanning those slides. So all those factors can make even the normal slides significant different. So how are we solving those challenges? We want those NERD to be adjustable. So what we do is we really adding additional slides if the training sample is going to be changed sometimes for the phase 2 of the training only. So we adjusting those reconstruction errors in order to updating the weights of the baseline PGAN model. That's you don't have to go back to the phase 1 and retrain the entire things. To save your money and save your time.
Right. Okay. There are no more questions in the chat box yet. Okay, thanks. Yeah, he says thanks. Yeah, how long how long did this paper take to finish? And were you already working in this domain?
So this type of research really takes the year by the Mayo and the Google partnership, and we have the main developers at Mayo. And we have the Dr. Gerrit here, the engineer from the Google side, to help to remove this part of the research, leveraging using the TPU resources and, from the Google Cloud computing resources to do it. But it's really a time-consuming project. Really takes a lot of efforts to complete.
Right. Okay, understandable. Another question is, can we avoid Resonant stage in pre-processing and create some other embedding matrix?
It's absolutely yes. So you can using the different methods to do the embeddings. Even you don't want to do it, it's also possible. What we would do is we think about this such a high resolution. You really want to reduce your memory size, right? Because you don't want to spend a bunch of your money while you're training those things, while you're already getting a satisfactory results. So that's one options we have, but we do leave the options for the users. But for example, if you train the images on the image, they definitely don't want to do the embeddings because the data sample is pretty small. That's just a toy one, right?
Right. Another question is, in PGANs both encoder and decoders, okay, is PGANs both encoders and decoders are set as trainable? How does this help in image generation?
So the PGAN usually just, even that's really progressive, let's just go back to the slide probably. So see here, so PGAN is just the traditional GAN architecture, but the only difference is here, they're taking the resolution from the lower and starting gradually increasing to high resolution. So the model architecture doesn't change. It's only with the one generator and one encoder. But for our model architectures, we need to do something different. We actually pushing this generator to act as the two functionalities. We make the generator be acting as the encoder first and then acting as a decoder. The discriminator always being involved in the kind of PGAN-based model architectures. So this version, the first one using the GAN functionalities to generate realistic images. Also, this auto-encoder architectures can prevent you from retraining the entire model if your data sets be changed.
I hope that answers your question, Anu. Yeah. Do you think, okay, yeah, we got it, thanks. So do you think we can proceed to the training part, and if you would like to share the repository of the GitHub, and if there are any more questions, we can come to them later.
All right, sounds good. Thank you. We just go to another screens. Okay, so what about now? Can everyone see this?
Yes.
Okay, so this code is a little bit complex. So we have a lot of lines of code, and it's impossible to work through all of them during this short of time. But what we do is we provide the user-friendly guides, documentations, and we have some of the notebooks for, because today I'm really focused on notebooks and documentation to just tell you how to using our code base to train the model and do the inference. So when you go to our main page of the GitHub repository, so first thing we will go to the notebook folders. We have the notebook examples being provided here. So I will walk through what those are for here. So we have the train GCP and train local. This is the two notebook examples for training the model. Train GCP is if you have the Google Cloud platform available in your institutions, so you or a person have access to it. So definitely this is what we need to follow. Or if you want to train this kind of model in a different computing result environments, so the train local will help you. So the same things here, we have the inference pipeline. So the inference pipeline is we leverage the Google Cloud Apache Beam Dataflow pipelines to do the inference through the Google Cloud. But the predict local is you can do the inference on your local machines. The loss logs is what we have, as I remember one of the audience asked a question how the loss experiments we have. Those is the notebook for you to really examine different loss experiments we have tested. So we have the documentation folders for the same things. Each of them were corresponding to one of the notebooks. So now let's jump into the training. So we are taking the GCP as examples. That is frequently used, and I think, but remember, all the parameters will be the same. Only the environment settings were a little bit different compared with the train local. We don't walk through all the required the packages because it's common for using the TensorFlow or some of the image packages required here. So this is the environment variable settings here. So remember, we have four phases of training. But the phase 0 is just the pre-processing. That's not a training. That's not a physically training phase, right? So we only have the 3 physically training phases. So that will be adding the generator training, encoder decoder training, and the discriminator training. So the first bit of the is for the generator training here. So we have different architectures being tested. Like the GAN anomaly is what we designed. And we also have leveraging one public available pre-existing called Burgers architectures. It's the first PGAN-based anomaly detection. So that you can choosing that, either one as your optional. So if you want to train the generator, for example, we can turn that to be true, otherwise it will be false. For example, we say that if you're adding additional slides for the training, you don't want to train the entire things, definitely you can turn this to be false. So we have the latent size, which is only available for us, some of the burgers and architectures. So we separate that between the different dictionaries. If you're using the burgers architectures, all the parameters required for burger is listed above. For the gain anomaly is in the bottom. But we have some common sense is for the loss functions, you will see the learning rates, the weights of the losses, those will be existing in both of architectures, and those are just tunable hyperparameters based on the user defined. So any questions regarding to this generator training examples?
No, all clear so far.
So then the same thing is for the encoders. We're doing the same things. They give you options whether you want to train it or not train it. So the hyperparameters will be also tunable, and the loss weights is user defined. So that's what allows you to do different combinations of the loss testing. We also leave you that for the different architectures based on the burgers or our design gain anomaly one, because you can really do the comparisons for the results. The last bit of the training is for the discriminator training. So this bit of here is the options that be seen here. The hyperparameters will be listed here. The weights of the losses and the architecture differences. It's all the user defined. So now we are jumping to the phase 2 and phase 3 of the training. So the reconstruction is how we train to learning the nerds. This bit here is we actually give you the options to call your data set. So for example, here you see the I in the range. This is also corresponding to the resolution. So we taking the 4x4 as the resolution 9, but the 1024 by 1024 is the resolution 1. So for example, if you're adjusting a different resolution, maybe the maximum be 512 by 512, so you will changing the range, probably going to change the -1 be 0 to make sure that's corresponding to the correct image levels. So we have the different, for some of the image information itself, like the channels, the depths of this, what is the height and width of the images, and which is the batch size of those things. And also we give you the options says for do you want to saving those trainable results in the different nature of levels, or you write out the results and at one single time, or just all turn to be false. So that's just some of the user-defined options. The same things for the error distributions. This is for the nerd training, and the same things for loading the data set, for the image information, reading out the results, writing out the outputs, several things. So this dynamic threshold training is really learning for the phase 3. So how you can setting up the based on the Hanover's distance or the other kind of distance options. What do you want to select in the threshold to flag out the anomaly pixels? But the same user defined options be the data set, what is the data set path, what is the image informations, what are those output things, or some of the hyperparameters for you to really jump into that. So then we have all the phases being combined. We're writing all the parameters into a big chunk of the training dictionaries and then loading them. And here is for the output dictionaries, which is whether you want to output those kind of output certain images to examine your results. For example, let's say I want to see how the generated images looks like, but you definitely will turning right output, export, encode generated largest generated images be true, but otherwise you won't be able to see how the generated images behaves. Right? So this will allows you to explore the model performance if that's really needed. So now those were the things just putting all the arguments here for the training and outputs information into a big chunk of information. And then we're writing all the parameters into the Python dictionary to a JSON file and loading that as a batch file to submit the job to the GCP. So we also leave you one option. I believe that is the benefits of this kind of notebook, because as you see, a lot of the parameters are being above here, but you cannot remember everything right by the times. And for example, I want to put in the majority of the things be defaults, but for some reasons I want to change some of them. we leave you option for the overrides. For example, it says, I only want to certain outputs. Probably I want to change the data resolutions. You can only just put in those specific parameters in the overrides dictionary. So what we do is we're going to updating those batch files based on the overrides, just overriding your defaults, right? Keep the parameters you done that's not listed there as to keep the defaults. So the job then will be submitted. So we also provide different options for you to submit the jobs running into the GCP using different GPU or TPU settings for A100 or V100 set roles. So that's all for the training examples. So from now, so any questions from the audience that's regarding to the training?
No, there are no questions, but yeah, the code is very detailed, very extensive. Now I understand when you said that there are thousands of lines of code, that's tough to do a walkthrough.
So we also have the inference pipeline here. So what we do is here, it's pretty, it's just doing the testing results. So this first bit of things is giving you the path to where the image is being loaded, where your input data is, where you want to output data being stored. So remember, we have several pipelines. Those are the things I really, I think this is interesting to introduce to the users. Because we consider several users may have several different needs. So maybe if you only have one single image patches or several patches, let's say, I want to test it, right? Well, I want to try your model and see how it behaves. So you can only given several image patches for the inference. That will run the notebook interactively without calling the data flow jobs. It turns out all the outputs you expect to see them, and it allows you to examine how the model really behaves. But for the use cases, they have an additional use case here. So for example, if you want to say, I give you the entire slide, can you do the inference for me? Right? I just don't know, I don't know how to chop up into different patches. Can you directly put in this entire slide and pass into the inference pipeline? Even that's usually we're causing out of memory issues. So to solving those challenges, what we do here is we call this will be the WSI decision pipeline. What we do is we take in the entire slide and doing the operations behind the thing. What we do is we chop out from the slide into different patches based on the resolution you have specified. And then we pass in all those image patches individually into the inference. And based on their pixel coordinates, when they're passing through the inference pipeline and getting the outputs, we stitch them the results back to the slide level and give you the stitch back images. That's what I show in the end of my slide. So this will allows you, so that means you don't have to care about anything. Just throw out a slide. We'll give you the results, whatever you need. But for the one additional use case is for the PNG individual. For some of the pathologists, they really have some software to already extracting the patches from the slide. So let's say, I don't give you slides. I just give you all the patches extracted from the slide already. So can you do that? What we do is we're saving additional slide for chopping out the patches. We're putting all the patches into the inference, and then we stitch them back the results based on their coordinates. So the output configurations here is all the outputs you want to check examinations. You can basically turn them be true or false, depends on your needs. So we also leave the inference configurations based on the user define. So that's I think the question they have asked me before is, do we have to using the Manhattan numbers distance? No, absolutely not. You can using the different distance computational ways. What is the threshold for the KDE? Can you specify it? Yes, you can. You also can change it during the inference. All the things are trainable. All the things are tunable during the inference pipeline. So I think this all does be clear, and those things are just where we're loading your models, where your models are being stored, and where's the outputs, and those things. So this will be really calling the inference pipelines and the job to data flow, and then this is a bit of the outputs examinations, how to examine the outputs, what it really looks like. So any questions by now?
No, none in the chat box either.
Okay. So if we don't get any questions here, so the one last bit of things is I will just walk you through with those documentations. because we say that we have thousands of lines of code, even that's impossible to work through entire things. But here's the documentation clearly to showing each of the parameters what that means. So we have explained those parameters in the plain English to provide enough details for you to understand what it really means. What is the options for you to tune it, to change the values of it. So if you have any questions, you can always refer to this documentation page for the help to really guide you how to use it. So I do believe that some of the people says, I want to change it using my own data set because they have different resolution, because we don't have the data set for what I provided. So we have the training and the inferences predicted on the custom data set and the training on a custom data set to really jump in to tell you what is the required parameters. You have to change it when you're using a different resolution images. So that which means if you just only give a different data set, but I don't care about the other things, those are things you must change. The rest things you don't have to care about at all. And you leave the be default, change those values, and then you're totally fine. Your model will be ready to execute it and give you the result. So all right, so from here, thanks again for giving me the opportunity to present here. It's great to talk to and have the code walkthrough with you. Thanks.
Yeah, no, the elaboration was great, even on the code, and you have been given so many options to try out with custom data set and stuff. So it would be interesting if anyone wants to, mold around a little bit and see if they can boost the results with something. There are so many possible experiments. You can try changing the distance functions and see how it pans out for you and stuff. Right. So it was great having you with us. And yeah, thank you so much for giving the talk as well. Right. So we're glad to have you with us today. And thank you so much for giving the talk, and best wishes from us. We hope to see a lot of more interesting work from you in future.
Thank you. Thank you all. It's great to talk to you today. Thanks.
Okay.
Good night. Bye-bye, guys.
Bye, everyone.